Wow.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning to all of the participants, and also good morning to our guest lecturer, Professor Yoshihito Shiono. Welcome to the guest lecture series today in the course of Organic Chemistry 2, and also to our department member and also the teaching team here. We're really grateful to invite you to join. Hello, Professor Unang.
Good morning.
Good morning.
Hello, Sensei. Ohio.
Ohio. Good morning.
Good morning.
Good morning.
Now in Surakai, getting colder, right?
Yes, getting colder. Yes, having a winter.
Oh, yes, I remember when I visited Surakai the first time, became surprised. Now in rainy session, Sensei.
Okay. Welcome to the guest lecture today, and also to the all the teaching team here. We are grateful to willing to join us on this lecture series of Organic Chemistry 2. And this is the first meeting from the second meeting, from the two meetings. And today we have Professor Yoshihito Shiono from Department of Wildlife and Environmental Science, Faculty of Agriculture, Yamagata University in Suruoka, Japan. He will give us a lecture titling Carbonyl Condensation. But first of all, I would like to read the brief curriculum vitae of Professor Yoshihito Shiono. Professor Dr. Yoshihito Shiono currently is a professor in natural product chemistry at the Department of Wildlife and Environmental Science, Faculty of Agriculture in Yamagata University, Japan. His educational background here, he spent his undergraduate, master, and doctoral course in the Osaka Prefecture University, Japan, under supervisor of Professor Dr. Hideo Hayashi. And his publication has already published in several high impact journal, for example, in Phytochemistry Letters, Tetrahedron, or in Organic Letters. And I think that's the brief CV of Professor Shiono. Now we will be listening his lecture. So for Professor Shiono, the time is yours.
Okay. Okay, thank you. Thank you so much for the kind introduction to me today. Yes, I also very happy to see you and Dr. Farawikindi and Dr. Desi and Professor Unand. I'm very happy to see you again
Rani also,
in this
Dr.
lecture. Dr. Rani. Sorry, are you Rani? Oh, good morning. Sorry, I forgot that.
Looks like students, yeah?
Yes. Also, all the students, the many students attending here. Thank you so much.
Dr. Rani likes undergraduate.
So yes, Dr. Rani always wearing glasses. Today you haven't glasses, so that I couldn't understand where you are. Okay, thank you. Yes, I do my best is to give today's lecture carbonyl reaction. Yes, I always the isolations, the compound and the structure determination. I don't use too much the organic reaction, but yes, today I want to give lecture. Yes, I do my best. So my lecture is the guidance with a textbook. So. And please open textbook and carbonyl. I forgot number that. Aldol reaction. Yes, there's the Aldol reaction. Sorry, is there? Oh, sorry, my page is getting overworked. So I turn off the video. It's all right. So okay, I just starting with the Aldo reaction. Yes. Okay. Next with the that's starting the Aldo reaction. This is topic, the one of the topic, Aldo reaction, and later is the Kreisen Aldo reaction next, and the Kreisen reaction, and the Michael reaction, and the Robinson annihilation. Today, if possible, I want to speak until the Kreisen reaction. So yes, the starting from the Aldo reaction, that's a very useful reaction because we can make the new CC bond. Yes, new CC bond using that two same molecule. Yes, that's why having the aldehyde moiety. And yes, at first, and this is the reaction starting with enriched, and that another S component is the secondary carbonyl like this, and this is easily reacted with that and the CC bond here. So this is the enriched and is called the nucleophile, and another is electrophile. Nucleophile is this one, electric rich here. Yeah, this one is a negative charge, and the carbonyl oxygen is a positive charge. This one always look for and call for, yes, look for the positive. Positive is the less electric density part, and this is another part of the carbonyl. This is the carbonyl, also like this. That's the carbonyl has the strong, yes, electric charge in here. This is the next carbon is a plus and a positive, less electron density. So this is this part of the electron rich, and easily this one is moved to here and connected and the CC bond. So it's called the Aldo reaction. Yes. So yes, very easy and very useful to make the organic compound. And but the several yes, from here and we're talking about the Aldo reaction and enriched, and another is another carbonyl component. Yes, and yes, next. Sorry, the Kreisen reaction, the Michael reaction always is related to the carbonyl group, and the ketone is needed to react with each other. And but the next, yes, I want to talk to you, and this one is next is the feature of the Aldo reaction. Yes, Aldo reaction, the name coming from the aldehyde and the alcohol. Yes, because aldehyde is changed alcohol. So that's the name is coming from the aldehyde and alcohol, and it's called Aldol reaction. Yes, this is the Aldol reaction in here. Aldol, that's the starting explanation that it's called Aldol reaction. Aldo reaction is important too. This means that the two acetaldehydes needed. And this is the starting the material, the molecule, the aldehyde or ketone. And the next is this position is called the alpha. This needs the alpha position. This needs several proton needed. This is alpha. These positions very high acidity, but it's easily to deprotonated here. And next, yes, we can say this is the basic condition and the water. And after the several steps, the reaction occurred. And this is the newly product, the Aldo reaction. After Aldo reaction, this compound generated. This called the beta. Yes, generally next to carbon from the ketone, alpha, and next in the beta is called the 3 beta hydroxybutanol, 1, 2, 3 in here. This is the 3 position hydroxy or beta hydroxyaldehyde, it's called. Yes, both we can say that this is the beta hydroxy carbonyl component. So that aldol reaction is called aldehyde, and change the in the alcohol, so that we can say that this one is the aldehyde alcohol. Here the aldehyde changed alcohol. So aldol reaction. Okay. And yes, 3-step. This is the mechanism Aldol reaction. It has a 3-step. The next step we can explain that using the guidance of the textbook. And yes, okay. Next. So this is the reaction there, and started with aqueous anion. It's needed. Okay, next. Okay. Yeah, this is the mechanism of the Aldo reaction. Yes, reaction. Yes, this one occurred the high. This one that is protonated from oxide. Yes, alkoxide, and this one at first yes takes a proton, and the proton is given to the electron is behind this carbon, and this one is called inerate. Inerated equilibrium condition. This is has the 2 stage, and what difference around here? This is the electron here, and this is the move to this bond, and this again, this the electron bond is back to here. It's the move to the oxygen, and they are existing the both both equilibrium condition is a tautomerism. This is called inerate. Yes, nucleophile. Yes, because this inerate is electron rich, and always to look for the is a nucleophile. Yes, and next step. This is the first step. Next is the step 2 and the step 3, and this is the inerate. Is here, for example, this one is also the nucleophilic attack. Inerate is here. Yes, we can both there equilibrium condition. The both okay. At first, the textbook use this type and take here. Yeah, because we can take only this time. If we can isolate this one is unstable. That's the move to this component. And if I isolate this one, this component is here. So it means that they are not isolated separately. They are existing both equilibrium condition. And this is here and the use here. So this is the electron rich, and this is called nucleophilic attack. Nucleophilic attack here. This is the nucleophilic here. Because this one is a positive charge. This is the ketone group is always the minus charge oxygen here. The next is here is that positive charge here. So under this one is a negative charge, and this one is negative with the move to the positive charge, and this is called a nucleophilic attack. And this a new C-sim bond in here. This is the negative charge. This is the takes the proton from H2O there. Yes, and this is also equilibrium, and this one is the yes, and this is generated compound that beta hydroxyaldehyde is generated. Yes, yeah. So this is a mechanism of the Aldol reaction. Yeah. Okay. The next, and next also the same, almost the same as before. This is the explain the using the nucleophile. This is the minus. Yes, this is the root for nucleophile attack. Here attack nucleophile attack, and this is reacting like this. Yes, this is in right, and this one is also the same as before that Aldo reaction explained that. Yes, so Next, this is the example of the using the propanol. This is the carbon number 1, 2, 3. Carbon number is 1, 2, 3. This is the deprotonation occurred in here. This is using the alkoxide in anion using. And this one that take the one proton in here, the one proton in here, but the place is only the alpha proton position here, the alpha beta. Yes, always always alpha proton is and that the proton is connected to the alpha carbon is very high acidity. Yes, because that electron is moved here, so that this is the minus plus positive. And this is the inlet. This is the inlet. Is a nucleophile. This is attached to the another is a propanol. Another propanol. This is always minus. This is the plus. This is attacked here. And this is the yes nucleophile attack. And newly the CC bond is generated here. Yes. Yes, and こうだな、こうでエノレイト、here、こうで、で、こうすると、こうだな。Yes. Yes. And this is the minus charge. Here to takes the proton from H2O, and the beta hydroxide, the aldehyde is generated here. Yes. This is a general Aldo reaction in here. This is the carbon, and this is the alpha carbon. This is connected and make a CC double bond here. Yes. And yes, this is a very useful reaction. Yes, they are using the starting the same almost as it's the Aldo reaction. They're using the two same molecule. Yes, the reaction with another molecule. This is the general Aldo reaction. Join these two C's together. Yeah. Next. Okay. Draw the aldol product from each component. Yes, we have to check the aldol reaction. Component. OH minus deprotonation, and this is the minus, and this one is attacked to the another same molecule here, there, here, there. ちょっとこれだと。Sorry, before that I did, but I lost where is the paper. Okay, so I can do that. に、こうして、あと、うん。B は SOC でカルボニル C、CH2 で COH で。Next also the same CHCOH. Yes, this is the Aldo reaction card, and CH2COH. CH. Yes, please try or you can do that. Yes, this is very interesting, very important. And here, and attack here, and code. Yeah, like this. Yes, please try that. So, and the problem is the 224.2. This is we have to choose which one the undergone and do not undergo an Aldo reaction when treated with OH minus and in H2O. We can choose that this compound because this one is alpha. As alpha position, there is this is alpha carbon. There is no the hydrogen. This is the no, so that this is the not reaction. This one also the here alpha. This is the alpha position. This is the proton, three proton here, and this is under this one also there is no proton in the alpha position. This is all the connected material, and there is no proton here. And this one the proton here. This one also the proton in here is reacted. So which one is the which carbonyl compound do not undergo an Aldo reaction? Either yes, the compound A, there is no alpha position, there is no proton alpha. Number C is also there is no proton with the carbon. This is the Aldo reaction. They don't react it in the Aldo reaction. Yes, because there is no proton in alpha position. Okay. No, chat. Okay, this is dehydrogenation of aldol product. Yes, aldol product is, yes, as I mentioned, aldol products to always the beta hydroxyaldehyde, because the hydroxy group attached to beta position. Yes, attached to beta position, and some aldol reacted to product actually will be the dehydrogenation is occurred in here, and to make the new conjugated product. it means the double bond inside the alpha and the beta position. This is the alpha beta unsaturated carbon compound. It's sometimes they happen this one there. Yeah. So especially the compound, especially this and line 2, and then the second is starting with acetophenol, and this is the beta hydroxy ketone is not isolated. Yes, in case of this compound is next to a beta carbon, this is the phenyl group is attached to here. This is very unstable, and this one is more stable than this beta hydroxy ketone. So this is not isolated. So this is dehydration is occurred, and the dehydration occurred, and this is the yes, of course there is that and the form is the cis. It means the cis and trans meaning on the double bond area. Yes, this can form there, and yes, this elimination of the HCO is spontaneous, and the beta hydroxy and hydroxy carbonyl compound cannot be isolated in case of that. Yes, next to the benzene ring, they're not isolated. This compound is isolated. Almost this compound is isolated, including the double bond. Yes, because this compound is more stable than this one. Yes. This the dehydrogenation is called the condensation reaction to the condensation reaction, that elimination of H2O. This is an example of the dehydrogenation of the Aldo reaction. And this one is the dehydration of the beta hydroxy carbonyl compound with base, yes, with base. Base means that OH minus or something, OH minus, not acid. Yes. So this is the Aldo reacted product. This is the base in here. It takes the proton here, and the electron is behind that carbon, behind this carbon, alpha carbon. And this compound, we can see this compound. This might move to the electron here. This is the deprotonation. This is the electron is returned to here, and the new double bond is generated here. Yeah. Here. So it is the kind of the mechanism of dehydration of beta hydroxy carbonyl component with space there. Yes, acid also the same thing. Same component is generated in acid condition to the later acid condition thing. And yes, the first step, the Aldo reaction. Second step, yes, electron pair inerate to form the double bond, pi bond as the OH minus is eliminated. Yes, this one. Yeah, this one is that also resonance stabilized is there existing the equilibrium condition, the both component existing here. Keto form and enol form. Yes, okay, next. And yes, this is a problem. What the unsaturated carbon, the carbon is formed by dehydration of each the beta hydroxy carbon component. So that's very easy. That's this one is the double bond attached to here. This is the yes. Now and this one also with double bond in here. We are always thinking that this is the next position is alpha and the beta. Yes, ketone, the next to carbon is alpha and next is beta. So the alpha beta the position is double bond inserted. Of course, this is the elimination is OH group. Yes, elimination is OH group. Elimination OH here. Yes, so that this is a and Okay, like this. And yeah, this one yes, last mechanism was the using the OH base, the OH minus, and this here is that acid condition H2SO ね。Yes. ちょっとお昼。H plus and SO4 H plus and HSO4 minus existing, and this one is that attached. This one is the take the proton here, and it's positive, and H, and here. This is the elimination of the H. And here, this is alpha proton, alpha carbon attached to the proton, alpha proton. Easily deprotonation is occurred, so that this is deprotonation, and electron come here. So that yes, same product. This product is produced from here. Yes, this is the normal. Yes, normal reaction we can. Yes, this component is generated in the acidic reaction. That's the same reaction occur in that and the basic condition and acidic condition. And yes, next is using the synthesize. So that check okay. This is a synthesize the compound using Aldo reaction. So this is Aldol reaction, one of the useful reaction to make the organic synthetic compound. Under the organic synthesized, yes, we have to think that, for example, this is the target, one of the target compound. This is the one of target, which reaction we have to use. Yes. So and in here is Aldo reaction. So we have to think what kind of which one is the starting material to undergo the Aldo reaction. So at first, the focus on the is the aldehyde group, and the next aldehyde, the carbon is alpha. So we can say this is alpha, and the next is beta. Yes, always. So that alpha, beta. Yes, please. Yes. So Aldol reaction always make the new CC bonds on beta and carbon, beta alpha carbon and beta carbon, so that we can think that this one is the alpha carbon, this is the beta carbon, so that we can cut this one, and this one is maybe the starting material. Yes. So and here the break the molecule into the two halves between the alpha and the beta carbon. Yeah. So that's this one is also, this is the material. This is the beta, is the before Aldol reaction is the aldehyde to change the alcohol. This is the back to aldehyde. This is the originally, this is the aldehyde compound. And this one also is the aldehyde. Yes, this is the starting right side. This one is the left side here. So they're the same molecule, and that's the same aldehydes, the two same aldehydes. So we can use this compound to make this compound. And the next reaction also, we are thinking the same procedure. We have to focus on this is the ketone group, and next is alpha, next the beta. Probably this is the dehydration is occurred, elimination the H2O, and this one this text is the break here. Yes, before that we may think that like this. Sorry, and we can imagine that this compound to alpha, beta, the break here. So yes, the two molecule of the cyclohexanone. Yeah. So we can make this called the retrosynthesis. So try to find out the synthetic pathways that we can think back to that. Yes, how to find that the starting molecule. This called the retrosynthetic pathway there. So we've run already Aldol reaction. We can make the retrosynthetic pathways using the Aldol reaction. Okay. This is one of the example. And what's the aldehyde and what are the aldehyde the ketone needed to prepare each compound by an Aldol reaction. So this one also is we are focused on this compound. Next is alpha, next is beta. Yeah. Which alpha, beta. This is the break here. So this one that we can make this one the aldehyde. So that the same two of the same molecule that's starting, and next to this one, yes, we focus. This one also is the aldehyde here. Next carbon is alpha, and next is beta, so that we can break here. Yes. Oh, and this one is aldehyde C8. Okay, and this here next to this compound. Okay. We'll focus on this is the carbonyl here. This is next alpha and the beta, and this is the double bond in here. This is the dehydration is occurs later. Break here. Here, yes, the same of the two molecule they are starting. This is the alpha proton in here. This is the alpha proton in here. This is the alpha proton in here, and this is the deprotonation, and this is the negative, and the Aldo reaction occurred here. Yes, we explained that how the Aldo reaction occurred here. Occurred and here. Okay. Aldol reaction always reacted with alpha proton. So we can make that, we can solve the problem. So we can solve this kind of the problem, not so difficult. And we want to move that. The next is the cross Aldo reaction there. Yes. Yes, cross Aldo reaction yes, so Aldo reaction, they're using the same aldehyde and the two of the same and the ketone used, and this one is a different, different type of that and the ketone and the Aldo are used. So that's the cross mean that the several type of Aldo reaction occurred and several type of the Aldo product generated. So this is very complicated. I think it's not a good way to use that, the cross Aldo reaction to organic synthesis, but improve the idea to solve this problem. This is a very useful strategy, useful and the technique to get to synthesize the compound. And this is the next is that Aldol reaction of the two different aldehyde. This is what example there. And there the problem in here, that's the both the having the alpha H atom. Yes, for example, at first we are focused on the acetaldehyde in here. This is the alpha proton in here, So this is at first inerate. This is the inerate, here. This is the reacted to the nuclear reaction. So for example, this one nuclear reacted is another acetaldehyde. Yes, this is also the aldol product. This is the inerate in here. This is another. This is the inerate. Sorry, this is the inerate here. And this is the coming from acetaldehyde in here. Okay, and in here, this is the aldehyde, that this inerate reacted with this one, yes, propanol. If the propanol reacted to propanol, yeah. So this is the inerate. Yeah, this is the inerate. This is the coming from the propanol. They are different compound. Yes, and furthermore, the propanol also alpha proton. This is the inerate here. Excuse me, there's someone coming. So on, and this is inerate from the propanol. This is inerate. This is also inerate the propanol. Inerate. Yes, and this is reacted with acetaldehyde. Yes, this is the compound that generated, and this compound is reacted with the propanol, another propanol, and this compound is Aldo reaction. So we can see that the four different type of the inerate is the Aldo inerate is produced. All were Aldo reacted product. They are different. So, and this is very complicated. So we are using the both two compound. Yes, having the alpha H atom. Alpha H atom means that the and the proton, the several proton on the alpha position. So this is the start. If we choose that's the both two kind of the compounds in the reaction, in the Aldo reaction, that we can get the four different type of the compound. Very complicated. If that reaction occurred 100%, but we have to separate our target the compounds by the column chromatography. So that we need a little bit so improvement needed to get our to do the Aldo reaction in case of this. Yeah. So here the conclusion when the two different aldehyde have the alpha hydrogen mean here the alpha hydrogen cross Aldol reaction is not synthetically useful cross so because that the whole different types of compound were generated in this the Aldol reaction. So this is not so useful. Yes, so because we have to separate here, and separate we have to take one. If I need this compound, the others are not important. So that the total the yield decreases. So that the good organic synthesis pathways, it's the yield is more than 90%. So that we have to need the more and high selectivity Aldol reaction. So because this one is the both the starting material is the hydrogen, alpha hydrogens. And next, this one is that synthetically the useful cross Aldol reaction, the improve the last Aldol reaction. Okay, last reaction. Only one, yes, only one carbonyl component that has the alpha H proton. In here, that's the controlling that the alpha protons the numbered. So for example, it's a starting, we choose the starting this type and this type. Yes, there is no alpha position the proton here, so that there is no the alpha proton atom in here. Yes, this is the quaternary carbon, sp2 quaternary carbon. This is only here alpha proton here. So and this one and this one is the alpha H. This is very reacted. This is the alpha position. So that make the N rate, form. Yes. So that's reacted this one. For example, aldehyde and N rate. Yes, they are coming from N rate, and this is the cinnamon aldehyde, is natural product, the component of cinnamon. Yes, good smell. This compound generated. This is the elimination of the hydroxy group is occurred in here. The cinnamon aldehyde in here. Yes. This the tip is the only this compound is from the N rate here. This is the controlling. Yeah, this one also starting the acetone. Acetone is here. The alpha hydroxy here. This one also are the hydroxy here. Yes, and this one I don't. Yes, I don't write the reaction mechanism. This one is in rate. This one is in rate. This is the Aldol reaction and the new CC bond attached to here. Yes, new CC bond attached here and the elimination occurred and these compounds are generated. Yes, this is the controlling the Aldol reaction. This is the very useful strategy here. Okay. Next thing here and example. Yes, please try. Please try all the students to please try. Yes, I also is try now, and yes, this one that and benzene and aldehyde is there is no proton here, alpha proton here. This one is the proton here. Yeah. So and after deprotonation here, here and this one is a target. That alpha. This is the minus. The reacted is aldehyde attack, and this compound here, and elimination here, the elimination of the water, and here it's here okay, and next year the draw the product from the each cross Aldo reaction. So and this one also the A. Okay, the here the minus is attached to here. Yes, and OH. Yes, and this one the same as before. The height and if the elimination occurred, we double bond in here, and yes, so this one also if the elimination occurred, so yes, and B, A, C, B, B, number B, 3B だこれか。ベンジンリング C65CO CH3 C3 and HOH. Yeah, こうで。で、if the elimination occurred, so ここでちょっと変だな。Okay. Probably not so difficult for you. Yes, please try by yourself. Okay, we move to the we move to next, and yes, this one is the same with the cross Aldo reaction, but the different components they're using. The one carbonyl component is especially the alpha acidic H proton, especially mean that this one is having the this is the normal yes, Aldo reaction, the reaction, one component. This one is that Z, Y, and Z. This is the Y and Z. Y and Z the having the both carbonyl compound or nitrile is attached here. So and for example, this was the benzaldehyde in here, and this one DHL, the malonate in here, and the production in here, like this. Yes, probably the next is that we can explain that reaction mechanism. This is difference between the difference from the last Aldo reaction. That's the one of the components. The one more component is a very highly acidic proton, because this is the alpha position. This is they say this is the high acidic position in here. That they say high acidic position because the Y and the X, both substitutes are ester or the aldehyde, or this one ester or nitrile. So yes, because this proton is a very high acidity, easily deprotonation occurs, and double bond is generated here. always and this is the reaction. This is the reaction compound. Always the beta hydroxy compound always lost the water to form the highly conjugated program. Yes. So as next we can explain that the reaction mechanism. Yeah, reaction mechanism the same as before. This one, the CH2 here, and the CO or ester attached to here, the same ester. And this is the alpha position. This is a very highly acidic position because this the proton is a minus. Electron charge is a minus, and this one is a plus, and this one is a plus. Very the highly high. This one is so and located the both ester group here. So this is the high acidity, and this is the alkoxide condition. And this is the reaction that occurred. This is the protonation occurred, and this is the protonation electron rich. This is the reacted with here. This is the nucleophilic attack. And this compound is I generated Aldo reaction, and this is the ethanol, and the proton is deprotonated from the ethanol, and here is here. This one is unstable. This the stable than this is the stable than here. Yes, because next to the benzene ring, here. And this one is still very highly acidic condition because the two carbonyl attached to this carbon, and easily deprotonation occurred. The elimination of water in here, so that and this one is the insert the double bond in here. So we use the when in this Aldo reaction we use this type. And ester or aldehyde or nitrates, the Aldo reaction always have a double bond in here. Yes, because the very highly activated is this alpha position the proton, because the attached to two carbonyl group in here. Not only carbon, nitroyl or aldehyde is okay in here. When to that starting material of this kind of compound, always the Aldol reacted product have a double bond in here. Okay. This is the also example. The ester or decay ester. This is the ester. This is the ketone group. This is cyano. This is nitrile nitrile here, and this is the carbonyl here, and the alpha position here, the very activated. This one also both nitrile here. This is the and alpha position is very highly activated. For example, this one excuse me. もう一度すみません、失礼します。Very excuse me. I'll back. So, starting in the cross-Aldol reaction, the phenylacetaldehyde, this is C6H5, and here like this, and this is starting material here, plus C2C. Okay, and this is the deprotonation occurred. This is activated. This is the minus, and reacted here, and yes, here and still the hydrogen here that this is alpha. It's the beta hydroxylated carbons, the component in here, but always the lost water from here. There's lost water from here. Because this one is still active. Yes, because the two and the carbonyl ester group that attached to this carbon, this alpha proton. So this one is generated component here. COT. Okay. Okay, and this one. Yes, next is also the, I think the same as the, yes, the same as before. B. Yeah, please try next. This one also that looks interesting, but the activate is alpha position with proton. Okay. まあ書いておこうかな。まあ、show the result かな。じゃあ、それは just only tell that only answer. Some student study later. Okay. Okay. And next は、そうか、これで、こうで N かな ?Is OK? OK かな、B, C. Okay. Next, okay. Next, useful the and transformation Aldo product, Aldo product. So, これか。あれ、same かな。OK, same page. Same page. The useful transformation. Yes, we have to think that. Yes, this is the problem with the 24.9. What the aldol product is formed when the two molecules, the butanol, react together. Presence of base. Yeah. What's the region needed to convert this product? This is a bit complicated, but I want to use it simply. Yes, this one that probably we can. Yes, very similar to the last component. Yes, the similar component appeared in the program before, and this one that I want to put here. yes, reform this one, and alpha and beta, I want to cut in here so that we can, so I can think this is the structure of this. So here. Yeah. So, so this reacted here. Maybe Aldo reaction occurred. So Aldo reaction occurred, and next is the this is the hint is that this the figure the 24.3 this is the chips in here. So that's the we can make the biosynthesis pathway or the in this is the program we need a chip to the organic synthesizer so that we can grasp that at the chip in here. So and so this is the oxy and reduction occurred in the pH4 the reduction, and this one they make the here there. Okay. Here and this one yes if I use the more the basic, this is the elimination is occurred. Elimination occurred. This is the Aldol product. Elimination occurred, and this is the compound C. This is the compound C. Yes, this is the compound. This is the compound A. Yes, the compound B is the there's the methyl attached here. The methyl attached here. This on the later we can explain that this is the Michael reaction, the additional reaction. Michael reaction. This one that appeared in here. Yes, this is appeared here. Michael reaction later we can next time I can explain this is the 1, 2, 3, 4 is the 1, 4 the additional reaction. This is Michael reaction, and this is the this is the Grignard reaction. Grignard reaction to make the compound C to A, B, C, D, and this one. Sorry, getting complicated. So this is the proton methyl H here. This is a Grignard reaction. You have already run this. You have already run this is the reaction. Is a Grignard reaction. That's the directly the reduction to the carbonyl position here. This is the Grignard reaction. Reaction. Yeah, this is they are the basic reaction, but very useful to make the structure. And yes, it looks interesting. When you have a time, please look for the suitable the synthetic pathway. And just I'm using the several reactions taking from the figure 24.3. Yeah. This is also the hint in here. Yes, when you have a time, please read around here. But very simple. Always very simple. Yes. And next, the directed Aldol reaction. Okay. Direct Aldol reaction. In here, for example, the prepare enrich the one carbonyl component with LDA. LDA, the very strong basic. Yes, very the strong, the basic. Yeah. And the secondary, that the secondary carbonyl component electrophile to disenerate. Yes, disenerate. And yes, and this is the one of the LDA selectivity to form the less substitute at the kinetic LNH. Yes, less substitutes, and we can show that later. Yes, this one that. This one the using result of the LDA like this, the same is the high and high base is the strong. The strong that takes the proton from the alpha position. This is the alpha position. This is the one in here. This is the proton is the two proton in here. Yes, which is a favorable for the LD8. So because in here this one is the CH3. CH3 that's the bigger than the proton atom. CH3, the methyl, that's the proton, and C. So we can like this is the methyl is like this, but the proton is very small. So this one is the hindrance. They come to the LD8, so that not access to here. Yes, because that's the methyl is attached here. But this one is a very much spaced bigger than this side, so that's LD8, the approach is very favorable. So here, this is the deprotonation that occurs in the alpha position. In this type, this alpha position is not this, because the methyl in here. So this is the one of the technique which carbon to attach to the another carbonyl, so that which the carbon is make to the CC bond. We have to select the starting material substitute, and this was the THF with the solvent, a kind of solvent. All the chemical reactions occurred in the solvent. Yes, at first this is the substitute, a substrate and solved in the solvent, and add that LDA is the base, and takes the proton in here, not in here, the proton in here. This is activated, and this one they reacted here, and yeah, so that the new CC bond in the here, like this. So yeah, so this is the very selective way to making this compound using the CC bond newly, but it's not here. Yeah, this is our yes. This is also modified by our desirable Aldol reaction. Yes, when we can change the starting material to the result to the difference. So that's usually the organic synthesizers, the checking this compound. Okay. And next. Just a moment, sorry. Excuse me. This is the natural compound isolated from the American cockroach. That natural compound is very amount is small, 200 microgram isolated from the 17,500 female cockroaches. So very much a lot of the tons, a lot of the humans collected, isolated, just only 200 microgram. 0.2 milligram. That's very tiny. So that's the way that the scientists want to have to confirm that structure. This is the starting the organic synthesizer. This is the needed organic synthesizer technique, and they can make the organic synthesizer. They can make this compound from the small available and the starting material. Then this component what is the easily available is the commercial component that is starting. Yes, this is the Aldo reaction is the use in the here. And okay, yes. Sorry. Here and yes, this one is the alpha in here. This is proton. This is the detonated. This is the activated here. Here in here, and next this one is Aldo reaction occurred in here. This is reaction in here. Yes. So this is the Aldo reacted product. After that, several steps needed produced here. Okay, this is Aldo reaction is very useful in this reaction. Okay. R mean that I'm not sure at this moment R is what, but the protecting is the primary alcohol. Primary alcohol very easy reacted, highly reacted rather than other functional group. So that's the protected by R. Yes, and the next. Here. This is the this is also very simple there. Yes. This is the ingredient of the curry. It looks like the yellow. Yes, this is the ginger. And yes, this is the breaks the moment. Yes, if we synthesize this compounds, what the starting material that we can use. This one is alpha and the beta. Yes, the beginning of the lecture, we think about alpha beta. This is the bond break in here. This is the make the enriched and the here. This is the Aldol reaction here. So yes, it looks easy. Yes, we also is run the Aldo reaction, and we can make the the strategy of the biosynthesis strategy of the organic synthesized using Aldo reaction. And here also that's the program again, and what the carbonyl starts the materials needed to prepare the compound using direct Aldo reaction. Yes, Aldo reaction. And in here, here that probably direct reaction occurred. Here, so, and next here. Yeah, and here. Probably the the elimination occurred in here, so we can make here. That's called here, and I guess everybody has the right answer. And next also, and this one is the one of the Donepe zero. This is the Donepe is the one of the Alzheimer disease. Yes, Alzheimer disease. This is the structure. This is the organic synthesized compound at the reaction they used, and carbon unsaturated carbon X. What carbonyl starting material needed to prepare X? Very interesting structure now, beyond our imagination. So Yes, this one reacted here. Yeah, probably the compound extra. Yes, yes, they found generated in the Aldo reaction. And next is the okay. Next we can move the intermolecular Aldo reaction. Aldo reaction. Yeah, this is also very interesting structure. Sometimes I stress this this the molecule, the intermolecular reacted product from the nature. Yeah, this one. Yes, and this is the most characteristic is that the D-carbonyl is a compound that can be used to make a 5 or 6 membered ring. So this is the starting material. It is having the 2 carbonyl position in here. This is the aldol reaction occurred intermolecule. In this the molecule. In this molecule, it means in this molecule, not intramolecule. Generally, that's it. This one is a 2,5 the hexagenol hexangion. 1, 2, 3, 4, 5, 6. So this one the 2 and 5. Yes. D the hexagion. Hexangion. D means that's the 2. 1, 2. Yes. 2, 5 the position. 2 and 5 the position. Yes. This is the redraw. Yes, like the same as this, the 1, 2, 3, 4, 5, 6. And using the basic and yes, activated. The mechanism is shown to the next. We move to mechanism shown to next slide here. Yes, yes, okay. Yeah, simply I can write like this or the here. This is the minus activated here. Attack is this is the carbonyl here, and yeah, and yes, so elimination occurred, and the double bond is attached to here, the alpha beta. So yes, we can see the step by step. This is the protonation occurred. The OET, very highly basic. This is the proton isolate, deprotonation occurred. And sorry, これ違った。Sorry, I missed it. In here, and here that's the and the electron is the behind the here. And this one, the redraw here like this. And this is the nucleophile. Nucleophile. This is attack to the carbonyl carbon. This is the electrophile. This is always the positive charge. This is the negative charge. This is the electric deficiency here. And this one is the new bond in here. And this one is the take the proton from ethanol. And ethanol is just minus charge, and take the alpha proton here, and unchanged ethanol. That's electron is the back here. So the proton and yes, hydroxy group, the removed hydroxy group there, and the two step and the elimination of the waters. Yes. And that's a newly CC pi bond means the double bond. This is the intramolecular Aldo reaction. The important thing that the new CC double bond here. Yeah. And okay, next. Yeah, this is a very interesting. Yes, so this one normally this is the predominant reach that generated here. That the more stable 5-member ring, usually five member ring or the 6-member ring. That is the someone think that if this is also alpha proton activated deprotonation and electrons to the to the attached to the this is the attached to this is the carbon. This is the cyclopropane ring that found, but this one is that is it possible? Is it possible? But this one is an unstable structure. This is not occurred like this. Even if it occurred, this is the soon the back to here because this is more stable rather than this one. This is not stable. So in here, this almost the reaction is this one is yes isolated because the 5-membered ring is more stable than this compound, the 3-membered ring. So yes, at first I mistook. The electronically here. This is also the alpha proton, but this is not favorable, unfavor and reaction mechanism, and this reaction is favor. So this one the dominatory, this one the more stable than this one. Okay, and this is also the 6-membered ring. This is also the we can make the same procedure, and this is the reacted here. This is the proton. This is the thing here. That's occurred. Yes, 6-membered ring, and that's newly the CC sigma bond, the single bond, and the double bond is a double bond attached to here. Attached to here, generated like this. Yes. This is the 1 methylene longer the last product. Last for the 5-membered ring. This time with the 6-membered ring. Yes, yes, this is the formation of this compound is the more stable, so that this compound is found, yes, generated in the Aldol reaction. Yeah, this is yes, getting that structure is getting the complicated. Yes, so this one is the first step is ozone reaction. The ozone reaction to break the double bond, and this one is the ketone group that produced here. This one and this one. Yes, and this is the using our around the Aldol reaction using intramolecular Aldol reaction. Yeah. This is the alpha proton here. It's activated, actually activated, and this one is reacted here. Yes, yes. Very structure complicated. Okay. And this is also in the deprotonation. Elimination reaction occurred in the proton. It's true. And this one is that. Sorry, I cannot write all of them. Yes. Okay, this one, the reaction. This is very interesting and useful the strategy to expand the ring, the 6-member ring. That before that the 5-member ring, and this one the 6-member ring is a very interesting as the mechanism of the Aldo reaction and the intramolecular Aldo reaction. Okay, this one, and draw the stepwise mechanisms of conversion that 2,6-heptane dione to the 3-methyl 2-cyclohexanone with natrium etokish and ethanol. So cyclohexanone two six and this one to the plus andでこうこれか。next here, top on the here. This one. Here, and this was the same as the ozone reaction using ozone reaction using and ozone reaction open. Okay. So yes, so but not so difficult. Probably you can do that. And this is the intra Aldol reaction. Yes, we have 20 minutes left, but I would like to close today's seminar. Today's class. I want to close, and so much for today. And we want to continue. I want to continue there. Yes, next is next 4th of November. Okay, thank you.
Okay. So should we have question time, or we can continue in the 4th, Sensei?
Yeah. Well, yes, I wanted to continue. That's my class on 4th of November. 4th of November. I want to close today.
Okay. So I think thank you very much for your comprehensive lecture today, Professor Siona. So we will continue your lecture on 4th November. Okay. Student. Thank you very much.
Thank you.
Yeah.
Maybe any more? Maybe some question from student.
Yeah, ada question, Kindi.
Okay.
So, can you read the question?
Professor Siono, we have some question here. Would you want to answer it now?
Question. Okay. What question?
Okay. Is it okay? Okay. This is question from your lecture today. So I think it's better than if we can answer now. There are, I think, 4 questions here in the chat room. I will read it for you. One of question is in Bahasa Indonesia, so I will translate it for you. The question from Elfrida. She asked that you explained that if 2 different aldehyde, which one from Elfrida? This one. Okay. If two different aldehyde have one, for example, alpha hydrogen, it means that a cross-Aldol reaction is not useful for the synthetic. Would you explain the reason for that? Thank you.
Yeah, probably the cross Aldol reaction there. So Aldol reacted product, several Aldol product generated. Yeah, so that in the text, whole different type of Aldol product is a same. So that we have to separate the with so that for example, the one of them are our favorable. I want to isolate this. I want to make this one. Other three is not important, not need for us, don't need us. So that we have to control the Aldol reaction. If we don't control that Aldol reaction, so that the total yield decreases because the others is not our target compound. Yes, I believe that if our target, both of them, that's very useful, but generally in that organic synthetic, it's the organist synthesizer that want to isolate the single component, high yield, but there is no selectivity, cross Aldol reaction. Yeah, so that's the starting materials, that's the both of them, having the alpha proton in the alpha carbon. Yeah, that is not good. Yes, because if we use the Aldol reaction of the two components, having the alpha protons, so that the 4 different type of compound were found after Aldol reaction.
Okay.
Yes, so probably yes, target is one of them.
I see.
If the reaction occurs 100%, 25%, yes, our compound, other is an unfavorable compound there. 75%. So it's not useful. Yes, of course. So that improved Aldol reaction, the one component having the alpha proton, others don't have the alpha proton. That's good there. Yes, because the alpha proton component activated by basic, and this one reacted to another aldehyde. Yes, component.
Okay. Thank you for the answer. I hope it's will answer from the Elfrida question. So I think we have another question here from Isma. This one, she has a question. You mentioned that when using the LDA, acidic proton will with less substitute will be taken. In this case, how if we use sodium hydroxide, will the acidic proton will be taken in both position?
Yeah. I haven't tried this reaction, but the LDA is very useful. That's the selectivity of activation of the both alpha proton. If I use the sodium oxide, possible we can use that. But the Aldol reaction, yes, there may be mixture. Yes, I haven't taken that, but theoretically, that's the Aldol reaction to the product, maybe mixture. It's not favorable. So that's the author of the textbook there, because they want to show that this is the one of the selectivity to make the Aldol reaction yielding the higher. So that's a very useful way, I think so. When you use the natrium hydroxy group, so the different side is the methyl, different is the methylene, the methine or methylene, the methine also attach the methyl. So that the methyl is the hindrance. Yes.
Okay.
It's okay.
Yeah, no problem. Okay, I think I hope that's answer. Would you want to continue your answer?
Yeah. Okay.
Okay. So that's I hope that's answer your question. Now the next question from Fred Lee. He asked about the use of comparison of sulfuric acid.
Sorry, I cannot listen. Sorry, I cannot.
Okay,
listen.
I will repeat the question. There are two ways that one of them, when the dehydration reaction occurs, there are two ways that one of them does not use strong acids such as sulfuric acid. Is the reaction rate slower than the reaction when we use sulfuric acid? And if we use strong base, what will happen? This is about the dehydration reaction.
Major reaction.
Yeah,
Oh.
dehydration.
The
So of-
hydration is
yeah.
generally it depend on the catalytics. If I use a lot of the catalysis, probably that the reaction and the better dehydration occurred. Yes, but the catalyst don't too much one more of that the limited to the catalysis that the beta hydro eliminations that don't react it.
Okay.
Yes, I think so. The amount of the using the catalytic in the Aldo reaction there. Yeah.
Okay.
Yes, the base acid is a. I guess acid is just only example. That's the program in here. It's not related to the Aldo reaction there. But generally the acid is not using the Aldo reaction there. Yes, so that's the also I want to explain that what the difference between the acid elimination there and the water, what the elimination of the water from the basic. Yes, that reaction mechanism are different. So that also I want to explain that once I want to think, once I make us to think about the mechanism of the hydrolysis, elimination of water.
Okay.
Is it okay?
Yeah. Thank you for your. I think that's answer student questions now. From the Gregorina, she asked, could we control the cross-aldol reaction to give the specific desired product? If it can, and how we control it, and then, or maybe should we add another reagent to control the reaction?
Reagent. So I can understand. Reagent.
Yeah.
Using an Aldo reaction.
Yeah.
Aldo reaction.
Cross-aldol reaction. How we control? If
how control that?
Yeah. If we want a specific product, for example.
Specific profile. Yeah. Aldo reaction. The cross-Aldo reaction. We have two components of the substitute, and but the one of them has the alpha proton. Another that doesn't have the alpha proton. So we have to combination of them. Yes. This is Aldo reaction, the very simple in here. So we have to carefully choose the starting the two materials. So one is the Aldo, one is the alpha proton. One is does not have another that does not have the alpha proton. So I think that's all. But I don't so much about the real organic synthetic experience too much. So yes, the students what we want to clarify. I want to understand well. But in textbook there, it's just only that we have to carefully choosing of the starting component. Yes, having the alpha proton or not alpha proton.
Okay, we have
That's okay.
Several. There are so many students ask you a question. Is it okay, right? If you want to ask this. And then another questions from Ahmad Fauzi. An Aldo reaction is a nucleophilic addition in which an enolate is the nucleophile, like the characteristic reaction of aldehyde and ketones. But I'm curious, can it be reached by the nucleophilic substitution or other reactions?
Other.
So probably he asked about the because the Aldo reaction is nucleophilic addition reaction. Nucleophilic reaction. Can we use another nucleophile? Probably he want to ask that.
Yes. My next class also I can explain that. Yes, Michael reaction or the Dickman annulation. This also that nucleophilic reaction. Yes, we can explain next.
Okay, this is for the next explanation.
Yes.
Okay. Okay. We have other questions here. Okay. From Muhammad Fakih, he asked about the synthesis of progesterone in the ozonolysis reaction. Is the function of ozonolysis only cleavage the CC double bond?
Yes, this is double bond. Yes,
Okay.
that's right. That's the very famous one there. When the students have the question, please look for that. This is the reaction on the website. Better than me. Very acquired a lot of information. Yeah, that's the very famous one. Yeah, yes, but yeah. So also, yes, I have the experience using that because yes, but ozonolysis. Yes, another reaction also to the is to break the double bond. But one of the the basic, the famous reaction. Yes. Ozonolysis. Yeah.
Okay.
But very useful, yes, reaction.
Yeah, it's about the ozonolysis because this is a very famous reaction. Yeah.
Yes.
And also, there's another question here from Selena. She asked about the, I think, intramolecular aldol reactions. Okay, wait. Okay, he asked about why only 5-ring enolate will form, not the 3-membered ring.
3-membered ring.
Yeah.
Oh, so
compare
that,
with 5. Yeah.
Yes, I will explain that. But it's better to read again the textbook there. That's the question that written in textbook.
So probably
so yes, maybe yeah, 5-member ring, the more stable run there. Yes, 3-member ring.
Okay.
Yes.
So she specifically asked why the 3-membered ring has a higher energy than the 5-member ring.
Yes, fire energy, the 5-ring ring, so that when you have a chance, you can make that 3-member ring, 5-member rings by using the modeling, and comparing the energy. Or that, yes, of course, that 100 is a very basic one. 3-member ring not so easy to make the cyclopropane ring. Yes, Dr. Kindi may have experience to try to make the 3-member ring. It's not easy. It's a modeling. They easily could break out. So it means they're very unstable, but highly toxic. If I get this compound, they're very highly toxic, very interesting structure. One of the so the cytotoxic compounds, they have they're having the 3-member ring.
Okay.
That's very highly, very, very interesting. Yeah.
Okay, so we have this is a student want to ask you directly. Is it okay? From the Angelica Kurnia.
Yeah, Pak.
Okay, so you can ask directly to Professor Xiong.
Okay. Thank you for the opportunity. Yeah, good morning, Professor. My name is Angelica. I'm sorry I can turn on my camera, and I have several questions to ask. For the first, if there are 2 identical cyclohexyl 3-octanon, which is a long chain of ketone that undergo with Aldol reaction, what should I do first, and what will be the product? And for the second, if the last
what material? Sorry, I couldn't. What starting material?
Cyclohexyl 3-octanon.
Cyclohexyl
3-octanon.
Cyclohexyl 3. Sorry, I couldn't understand. Cyclohexyl.
Which part you want to ask?
Which part?
The first question is, what should I do? Because it's a long chain of keton, what will be the product? And the second question is related to the first. So it's if the left compound doesn't count as maybe the alkyl, is it just disappear or also reacted with the Aldol reagent?
So you mean this the cyclization or what?
Yeah. My first question is, what should I do first with the reagent, and then what is the left compound, and is it also used in Aldo reaction, or is it just disappear or doesn't count, or what? Thank you, sir.
Sorry, Hindi, sorry, I cannot
So sorry.
understand that. What
I want to.
So,
me too. I not so.
so don't know.
But the first question is what molecule that you asked, Angelica?
Two identical cyclohexyl 3-octanon.
Cyclohexyl.
Which part did you say there?
Two identical cyclohexyl propanon. Cyclohexyl.
Two identical cyclohexyl 3-octanon.
Cyclohexyl 3-octanon.
Cyclohexyl. どれだろう?
Yeah, maybe this is a one cyclic compound substitute with octanon, right?
Mungkin gini aja ya Pak ya. Jadi kan oktana nih.
Iya.
Terus kan di yang paling kiri atau paling kanannya ada sikloheksana. Terus di yang C ketiganya itu ada keton kayak gitu.
Jadi dion itu tuh senyawanya?
Enggak Pak, satu. Ketonnya satu. Atau saya on ini aja, share screen aja.
Boleh.
Sebentar. Nge-lag, Pak.
Bisa share screen?
Nge-lag.
Nge-lag.
Sebentar.
Professor Siono, could you wait for a moment? She want to share the structure that she made.
Maybe I don't pronounce it correctly. Jadi ya.
That is okay.
Ini.
Yeah. It's shared now.
This one. You asked about the specification or what?
Ya udah Indonesia aja maaf Pak.
Yes, okay.
Balelo. Jadi kan reaksinya yang saya tahu reaksi yang tadi itu berlangsungnya kalau metilnya pendek gitu Pak. Kalau ini kan agaknya rantainya panjang. Reaksinya jadi kayak berlangsungnya seperti apa? Terus kalau ada rantai seperti ini yang pertama kali saya harus lihat itu apa? Dan kalau misalnya yang dipakainya segini, apakah yang ininya menghilang atau dipakai juga untuk bereaksi lagi seperti itu?
Oh, oke. Ya, nangkep. So, I'm sorry, Professor. Let me translate it to you. So, she specifically asked about these molecules because this is a large molecule, as you can see here. In the right, they are cyclohexyl group, and the left we have N-butane group here. So, I think she asked, can we use these molecules for the reaction? I think. Because in your previous example, you show very small molecules, maybe.
Aldo reaction.
Yeah, for the
Yeah, I
Aldo
think
reaction.
so. This should happen Aldo reaction.
Okay.
Okay.
And how about the specification, the position of the Aldo reaction, because this is have two alpha carbon. Yeah.
Well, I'm at this moment, I'm not sure. I want to ask the hard. I asked how many aldol reacted product, how many aldol reacted produced using this compound. I want to ask her again. Yes, why she want to ask her that? What she want to clarify? Yes, yes, I want to ask her how much, what type of different aldol reacted product when she used this compound as a starting material. Probably a good example for her. Yeah, it's a good chance for her to think herself.
Okay.
Yes.
Okay then. So I think she meant that this is have two different carbon. Maybe she want to ask about which alpha carbon, the alpha proton. This is have two different position for alpha proton, and which one will, for example, I think the major product if this compound react with aldol reactions, probably.
Well, at this moment, I don't know that which the proton is highly activated. But
Okay.
but the please, yes, I want to ask the please, yes, please clarify what is your target compound.
Oh, I see. So
yes, so that yes, if she had a target compound and what is the yes, so yes, a starting material is suitable for the target compound.
I see. So we
Yes,
have to know first the target, and then we
yes.
can set the, for example, experiment how to.
Yes, probably always the organic synthesizer. Yes, as you know that there are a lot of the mechanism and many kind of the Aldo reaction the product is generated, but it depend on the yield and it depend on the condition. Yeah, so that yes, so yes, if she has a target compound, yes, please look. Please consider again which one very
because
suitable.
She asked for very specific molecule, right?
Yeah.
Okay, then I think for the next questions, there are one student also want to ask directly to you. Is it okay?
I'm sorry. Thank you for answering, sir.
Okay, so this is the another student want to ask, April Sabranti.
Okay, thank you so much, Professor, for the opportunity that given to me so I can ask my question. And also, I want to apologize because I can't turn on my camera right now. First of all, let me introduce myself. My name is April Sabranti, and I'm from class B. So in your explanation before, especially in the example problem, you stated that a carbonyl compound without an alpha hydrogen can undergo Aldol reaction. So my question is, why an alpha hydrogen is very necessary or very needed in this reaction, and why a carbon compound without an alpha hydrogen can undergo an Aldo reaction? I'm sorry if you have explained this before, and thank you in advance, Professor.
Yeah, probably you can find the answer in the textbook there. You can read the textbook better than the listen from my explanation there. Yes, the carbonyl is always carbonyl the ketone very special function is oxygen is a rich electron, and next to carbon is a positive charge, electron deficiency, and next is the negative, so that's the alpha carbon always negative, that the electron is charged, so that easily the protonation occurred. Even if the protonation occurred, that the electron is stable on the alpha carbon position. So this is also one of the yes, a good function as inert. Yes, and the alpha carbon next to the carbonyl ketone, and the electron is moving and next to the carbonyl ketone. So that inert also the so an equilibrium condition, we cannot get isolate the one of inert. They are existing two types of them, but not completely definitely two types. They are yes the mixture like the yes the average compound is called inert, but we can write down the structure correctly in the textbook. So that the textbook always the yes the keeping the both structure. But actually, the compound we cannot isolate the one of them. They are existing in both. Yeah, this is a very special functional group of carbonyl ketone. Yeah. So, and this is a very highly the nucleophile inert.
Okay. Thank you. I hope that's answer the question from student. And then this is, I think, the last question. From the Jennifer, she asked about the reactivity of beta decarbonyl compound compared with only one carbonyl. She asked why the reactivity of or maybe the acidity of the hydrogen alpha in beta dicarbonyl is the more reactive than the monocarbonyl.
No.
Yeah.
So the carbonyl is a yes ketone group is a very special function that they are the strong the absorbing the electron moiety, and if the when it compares the one or two, yes the ketone group is attached to the alpha proton. Alpha proton the doubly activated double is the yes because the yes ketone group is a very strong the absorbing or the is electron. So that the when it compared the alpha proton have the one carbonyl and the two carbonyl and which one is activated, so that both is better than one. So that and the dicarboxyl, two carboxyl or the two ketone, two ester, the group is attached to the one alpha proton. So alpha proton is activated, double it. Yes, that is the stronger than one. So it means that highly reaction.
Okay, so this is I think she asked for another part about the how we make the difference between the reaction the Aldol cross Aldol reaction and another Aldol reaction. So maybe you explain about
yes.
there are 4 different type of Aldol reaction. Maybe she want to ask what the difference when we use the specific reaction for the compound. How you
yes.
How you choose one from the another for
another for that. Is it okay? I mentioned before that the one of them are having the alpha proton, and the other doesn't have the alpha proton.
Okay.
It's okay.
Yeah. Okay, so maybe I don't know. The question is not so clear. It's not so specific here. She asked in Indonesian, but I think that the point is you have to has the alpha proton in the molecule if you want to do the Aldo reaction. Right?
Yes.
Okay, so I think there is student want to ask another question because we still have time. 3 minutes left.
Still time.
Okay.
One more question.
One more question, please. Especially from student.
Kayaknya udah nggak ada.
Okay. Okay. So I think that's enough for the lecture today. The time is almost up. Thank Professor Siono for your lecture and your answer for the student questions today.
Thank you.
Thank you
Thank
very
you
much.
so
Hansai.
much. Thank you so much.
Thank you so much, Professor.
See you.
Your nice lecture.
Very sorry that I cannot explain well.
No, it's a very good explanation, I
Sorry.
think.
Sorry, maybe it's maybe difficult for the student to listen my voice. It's better than read your text.
How about the next lecture?
Next lecture at same time of the 4th of November.
Yeah,
Okay.
November 4th, okay?
November 4th. Yeah.
thank you so much.
Thank you. See you. Thank you so much.
Okay, see you.
See you.
Next
See you, Sensei. Happy nice day.
Thank you very much.
Thank
Professor
you.
Siono.
Bye.
Thank you.
Okay, for November 4, I think Kindi, can you help me to become moderator again?
Yes.
Okay.
Okay, no problem.
Okay, thank you so much.
See you on the same
Many
Thursday.
participants. Thank you.
Yeah, thank you. We will see you again.
Bye.
Bye.
Una.
Hi.
Oh,
Right.
that's
So
all.
yes. Next class. Next class. Just
Yes.
only giving a lecture. Okay. Next class. Just only giving a lecture. I close.
It's
That's
good.
okay. Now. I don't give the program now. It's okay now.
Okay, I think.
I think it's,
Okay,
it's okay.
It's okay.
Yeah,
Yeah,
I don't want to do too much. Yes, but yes,
No problem.
I don't need to evaluate them.
No need.
No need.
Okay, thank you,
Yeah.
thank you. Okay, that's like okay, thank you.
We can do to evaluate our student.
Yeah.
Sorry.
By ourselves. Yeah. Yeah.
Okay, see you. Thank you so
See you
much.
next Thursday,
Yeah,
Sensei.
Thank you.
Bye-bye.
Bye bye.
Ya, nanti mahasiswa Kamis masih dengan Pak Siono ya. Ya, langsung aja nggak apa-apa ya Pak Kendi ya, ditutup aja ya.
Oh iya, silakan. Oh, jangan lupa absennya mahasiswa.
Oh, iya.
Yang hadir kayaknya nggak 4 kelas ya, Bu ya?
Iya, tapi ini di-record nanti ketahuan. Bahkan yang tadi nanya juga sudah ketahuan juga siapa gitu ya.
Oh iya.
Tadi udah di save chat search-nya ya.
Oke.
Oke.
Itu segitu aja ya Ibu ya buat tim
Kamis
teaching
nggak
semua.
boleh ini ya, Pak Kendi ya, nggak boleh telat-telat lagi ya.
Iya, karena Prof. Siono juga tadi hadirnya bahkan sebelum
Betul.
kelasnya masuk ya.
Jam 7 ya.
Iya. Tolong mahasiswa semuanya ya. Perhatikan waktunya. Oke, segitu aja Ibu ya. Hatur nuhun. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih ya Pak Kendi sudah jadi moderator. Terima kasih Bapak Ibu dan mahasiswa juga ya. Saya tutup ya Zoom-nya.